So in this video we are going to continue to talk about the half bridge inverter. Just to make a clarification, I made a mistake in the previous video. I inverted the two values of the inductance and the capacitance. So the inductance should be 28 millihenry instead of microhenry, and the capacitance should be 6 microfarad instead of 6 millifarad. Purely by chance the output was acceptable, but these are the correct values. So in this video we would like to know about the harmonic content of the output waveform, and to remind you, we had a sine wave of 50 Hertz with 220 volts of root mean square. We can run once again the simulation, and in this video I would like to show you a nice function that LTspice provides us, which is the fast Fourier transform of the output waveform of any waveform of the circuit. In this case we would like to compare the output waveform, so the filtered output waveform, with the unfiltered one. Let's first plot the unfiltered output waveform. We can zoom in and we can see the square wave, basically the switching frequency that is given by the two switches of the leg, and we can see that is an ideal, of course, switching form. We don't have any rise time or fall time, and also we don't have any dead time in the switches. We can see it here because I put the reference in these two branches, but there is no dead time between the two switches, which are ideal. So now we would like to use the fast Fourier transform to see effectively the harmonic content of this circuit. And what do we expect? We expect a first cluster of harmonics at around 5 kHz, which is the switching frequency. As I told you in the previous video, we know that for an inverter the first cluster of harmonics is always at the switching frequency. So a good design parameter is to have a switching frequency which is high in respect of the output frequency to filter easily the harmonic content, and we cannot have a too high switching frequency, because we know that for this switching circuits and devices, the switching losses in the components is the one that is more dominant at higher frequencies. So let's plot the fast Fourier transform. We will go to view and then fast Fourier transform. We can use the default values in this case, and we plot the voltage across the output unfiltered. So we can see that we've got a 40 dB amplitude of harmonic content at 50 Hz, which of course is the output frequency that we want for the sine wave, and we can say that we have a lot of harmonic content in the higher frequencies, and these are the multiples basically of the switching frequency, because we've got a at 5 kHz we've got an high amplitude content. Also we can say that there is always a symmetry between the two spikes of the harmonic content, This is from the theory of the inverter we've got, and for also the symmetry of the waveform. So we've got a big spike at around 50 dB at 5 kHz. And then the other one will be at 10 kHz, which is a multiple, at 15 kHz, 20 kHz. Of course, the amplitude is decreasing. And so this is the harmonic content of this inverter topology. Now we can delete the trace of the unfiltered output, and we can see the output waveform. Let's fit to space, and we can see that it is a almost perfect sinusoid, almost perfect sine wave. And we have some ripple, of course, because even if the topology is ideal, this switching frequency is, of course, this switching function that is produced by the two switches is nonlinear, so we cannot have a perfect sine wave. We've got some ripples superimposed on our sine wave at 50 Hz. So let's fit to space and plot the fast Fourier transform of this node, and now we can say that the harmonic content is almost perfect. We've got the knee of the amplitude curve at minus 3 dB basically. It should be at around 400 Hz, which is our cut frequency of the filter, which is respected here. So, and we can see that there is also a spike at 5 kHz, 10 kHz, 15 kHz, but if we zoom in, note also in this case we've got the symmetry of these two spikes. We can see that the amplitude is very low, is 1 dB, is 5 dB basically, instead of 50. So this is the fundamental action of the output filter, to clean the harmonic content, because harmonics significantly increase the effective value of the current, the root mean square, and if the root mean square is higher, the devices and the components will need to be rated more than the actual current that we need. We basically need to oversize our components, because the harmonics is basically noise, and if noise is too high, it will be creating a lot of losses in our circuit. So that's all for this brief video, and in the next video on the inverters we would want to look at a ohmic inductive load without this filter capacitor. So we will see that the filtering action will be made just by the load. Okay, if you have any questions, let me know in the comments, and if you found this video to be helpful, share it and consider subscribing to the channel. I'll see you in the next one.